right, welcome to the second part of static equilibrium. Good boy, Wicket. Welcome to the second part of static equilibrium. I wanted to go over that second model problem. Wicket, hey, come here. Down, down. Sit. Hey. Yes, good, wait. I wanted to go over that second problem from static equilibrium. It's on page 498, 499, and 500. It takes up 3 pages. So the first one we did on static equilibrium talked about a guy standing on a ladder. That will be typical of one of the types of static equilibrium questions that I would ask. Another typical kind that I would ask, I call the sign question. This is slightly different, but still asking this for the same types of things, dealing with the idea of static equilibrium. I have a dog eating a book. Okay. So at the bottom of page 498, it says you have an 18 kilogram sign. So the mass of the sign is 18. And it hangs symmetrically from a 7.8 kilogram rod. So the mass of the rod is 7.8 kilograms. And I'll draw a diagram of this after so that you can see what they're talking about. The length of the rod is 1.3 meters and is attached to a wall, and there's a cable that makes an angle of 35 degrees with the rod, an angle of 35 degrees with the rod, and it helps to support the rod at the end, and they show you a picture. So you have a wall. You may have seen these, especially if you've been in a larger city. Sometimes they, rather than have a sign right attached to the wall that's flat against the wall, they'll actually have a rod sticking out with the sign hanging down high enough so that people won't hit it, but it's just more in your eye line so you'll see it better. So here's the wall, okay? And then there's a rod out here, and they said the sign isn't hanging at the end of the rod. They said it's hanging symmetrically. So here is the sign. So it's hanging so that it's balanced along that rod. And it says there is a cable attached to the end of the rod, and the other end is attached to the wall, so it makes a right angle triangle, and it's holding up, so this is a cable, and what it's doing is it's helping to hold up that sign. It's helping to take some of the support, because the other place that is supporting holding this sign up is here where it is attached to the wall. Wicket, stop spinning. You have too much torque. Go the other way. Get some negative torque going. All right, so the question that they ask is, what is the tension in the cable? So what is the force of tension in the cable? And what force is the wall exerting on the rod? So we're going to break this apart and look at all the different forces that are happening, in what direction and how. Now remember, we can only look at forces in the horizontal direction and then forces in the vertical direction. We can't put those together, but torque can go together all the time. Okay, good boy, Wicket. So there is a force of gravity pulling on the sign, down. There is a force of gravity pulling on the rod as well. Those are separate. There is a force of tension on the cable, and it's holding that sign up, so it's going that way. Now, the one that is confusing, the one that is different, the one we haven't actually dealt with too much yet, is the force that the wall and the rod have on each other. The wall is exerting a force, but it's not exerting a force straight up, and it's not exerting a force straight out. It's actually actually exerting a force kind of at an angle. So what we have to do is we have to break that force apart into its components. So I'm going to say there's a force of the wall, the X component, and it would be going that way. And again, it's kind of holding the sign out. If it was pulling the sign in, the rod would be sinking into the wall, and it's not doing that. And there is a force that the wall is exerting up as well, because it's holding the sign and the rod up. So there are 5 different forces that we have going on here. So again, we're going to be looking for the force of tension. Notice that force of tension, though, is at an angle. It is not straight in the X or the Y direction, so that's going to create fun for us. And the angle that the cable makes with the rod is 35 degrees, so that goes right there. So what we have to do is, first, we're going to look at torque. Remember, anytime you have a force, you also have a torque. So we're going to break these apart into different torques, and we're going to talk about them. Now, what we're going to imagine in terms of trying to decide whether the torque would be positive or negative, what we're going to imagine is that the wall and the rod, that's where your hinge is. That is your pivot point, okay? So we are going to have a torque because of the wall in the X direction. We are going to have a torque because of the wall in the Y direction. We are going to have a torque because of gravity on the sign. We are going to have a torque because of gravity on the rod. And we are also going to have a torque because of the tension on the cable. Wherever there's a force, there's a torque involved. So we have to look at each one of these separately and figure them out. Luckily, most of them are pretty straightforward. First off, the torque because of the wall in the X direction. Well, remember, torque is R times force. I don't know what the X component of the force of the wall is, but actually it doesn't matter because my R, remember, is the distance between where the force is being applied and where the hinge or the pivot point is. Here, the force is happening right here, the pivot point is right here, so my R is 0 anyway. So it doesn't actually even matter whether that's positive or negative because it's going to be 0 anyway. However, if I was thinking about it, if the rod was being pushed that way, it would likely start to spin this way, which would be clockwise, and so I would probably make it negative. Torque because of the Y component of the wall force, well, that's pushing up. So again, think if there was nothing happening, if I was pushing up on the rod, it would start probably spinning this way, which is clockwise. So again, I would probably make it negative, and it's R times F. But again, that force is happening right where that pivot point is, and I'm losing my voice, guys, sorry. That would be 0. The R would be 0, so it doesn't really matter what the force is because that's 0. Now we're going to talk about the torque because of gravity on the sign. Gravity on the sign is pulling down. If I was pulling this rod down, that would actually create it to move in the clockwise position, which is negative. So it's negative R times F. Now, my R is my distance from the hinge point to the force. Remember that we always think of forces happening at the center of mass, and we're assuming that the sign is centered on the rod. So if the rod is 1.3 meters long, halfway would be 0.65. So my R is 0.65. My force is the force of gravity on the sign. The sign is 18 kilograms and gravity is 9.81. Now we have to think about the torque because of gravity on the rod itself. Same scenario, if it's pulling down, it's going to pull it in the clockwise direction, so that is negative torque. I put 0.5, I should have put 0.65, sorry. Again, we're assuming that gravity is working on the center of that rod. The center is at 0.65, so that is our R. And gravity is the mass of the rod, which is 7.8 times acceleration due to gravity, which is 9.81. Finally, we have torque because of the force of tension on this rod. So again, thinking about force of tension, if that was the only force, it would pull the rod this way, which is counterclockwise, so that is positive torque. The R, well, the force is actually happening, and I'm just making sure I'm saying this right, that's all. Yep, the torque is actually happening 1.3 meters away, but think about this. Here's my force of tension, and I know that this angle is 35 degrees, but we said that the R always has to be perpendicular to the force. So if the force is going this way, perpendicular to that would be the R. So I can't draw this very well because, hey, it's drawing and I suck at drawing. It's probably better if I do this. And so there would be a right angle there. And so if my force of tension is that way, my R would be here at right angle to it. This length is 1.3 because that's the rod. So if I'm looking for my R, that is the opposite side over the hypotenuse side, so that is sine. So I would say sine of 35 degrees is R over 1.3. So my R is 1.3 times sine of 35 degrees. That's my R. So here when I'm doing torque, and I'm running out of space, so I'm going to write it down here, is 1.3 sine of 35 degrees. That is my R. My force, I don't know. My force is whatever this force of tension is, and I don't know that. But I know that this sign better be in static equilibrium. The sign should not be moving. So therefore, that is my only unknown, because that's gone and that's gone. And so this would be algebra, and I'm going to need a calculator and an eraser. So this would be algebra here. I would end up doing force of tension is, and I'd move that over, so 0.65 times 18 times 9.81, and I'd move that over, so plus 0.65 times 7.8 times 9.81, and then I'm multiplying, so I'm going to divide by 1.3 sine of 35. And what that should give me in the end is that should give me my force of tension. So if I do that, 0.65 times 18 times 9.81 plus 0.65, whoops, let me do that in brackets, plus 0.65 times 7.8 times 9.81, and that's all divided by 1.3 times sine of 35, and I get 237. They get something slightly different than I do. I don't know why. Did I put something wrong into my calculator? Because all my numbers are the same. Maybe they made a mistake. Let me redo this. 0.65 times 18 times 9.81 plus 0.65 times 7.8 times 9.81 divided by 1.3 times sine of 35. Yeah, this time I get a different answer. So I must have put a number in wrong. So force of tension I get is 220.63. So paying attention to significant figures would have to either be 220 or, thank you, 220 or 2.2 times 10 squared newtons. So I have the answer to one question that they asked me. So they asked me, first off, what was force of tension? So I used all the torques to figure that out. So it would be 220 newtons. Now, the other thing they asked me for is they asked me for what is the force that the wall is exerting on the rod. Now, because it's a force, we're going to need a direction as well as a magnitude. So we have broken it up into components. So just like in the last section, sorry, that is my 14-year-old dog coughing. Because this is broken up into components. Oh, Gabriella! Sorry. Because it is broken up into components, we're going to have to figure out what each component is, and then we can use the idea of Pythagorean theorem to figure out the total. So, first off, we're going to look at the x direction forces. So we're going to look at the x direction forces first. There's actually only two of them. There is the force of the wall in the x direction, which we will make positive because it's going that way. And the other one is actually the force of tension, the x component, because again, that force of tension is going at an angle, so I can resolve that into an x component and a y component. Now it's going that way, so I'm going to subtract, and again, it should be in static equilibrium, so it should equal 0. So the force of the wall, the x component, is equal to whatever my force of tension, the x component, is. So how do I figure out what that force of tension is? So we have the force of tension. We know it now because we figured it out in the last one. The force of tension is 220.63. This angle is 35 degrees. So this would be my force of tension, the x component, and this would be my force of tension, the y component. So this is adjacent over hypotenuse, so that is cos. So I would do 220.63 times cos of 35 is my ftx. So the x component of the wall is also 220.63 times cos of 35. Notice I'm not using the 220, I'm being more specific than that. And in fact, I have not even, you can't see it, but I haven't even erased the big full answer off of my calculator so that I can continue to use it here. So I'm going to take 220.63144485, which is in my computer, my calculator, and I'm going to multiply it by cos of 35, and I'm going to get that the x component is 180.73. Okay, so the force of the wall, the x component, is 180.73. Normally I would just leave this on the board, but we're running out of space because I have a little itty bitty board. So now we have to look at the y direction forces. So we're going to look at the y direction forces. What forces are working in the y direction. Well, pushing up, we have the y component that the wall is exerting. It's holding the rod up. We have the force of gravity on the sign. That's going down, so it's going to be negative. We have the force of gravity on the rod also going down, so it's going to be negative. But we also have the force of tension, the y component, and that is helping to hold the rod up, so it's going up. So plus force of tension in the y direction, and again, that should all equal 0. So if I move everything over to the other side, except for what I want to know, force of gravity on the sign would be the mass of the sign, which is 18, times 9.81. It's now positive because I've moved it over to the other direction, on the other side of the equals. So force of gravity on the rod is going to be 7.8, because that's the mass of the rod, times 9.81, plus Ft(y). Well, Ft(y) is the opposite side, so it's going to be 220.63 times sine of 35. That's going to be Ft(y). So Ft(y) then is not going to be plus, it's going to be minus, because I moved it over here, so now it's minus 220.63 times sine of 35. So I'm going to put all that in my calculator, and it should give me the y component on the wall. So 18 times 9.81 plus 7.8 times 9.81 minus 220.63 times sine of 35, and I get 126.55, which is what they get to, so that's good. And again, because it's going up, it's positive. All right. So now what we're going to do is we're going to figure out what is the overall force that the wall is exerting on the rod. And what it is it's the Pythagorean theorem. This squared is equal to the x component squared and the y component squared, because it's just Pythagorean theorem. Again, x is going this way, y is going this way, that creates a right angle, so the total is here. So we're going to do 180.73 squared plus 126.55 squared. And then because I want the force of the wall, not the force of the wall squared, I'm going to take the square root of the whole thing. And so the force of the wall is 180.73 squared plus 126.55 squared. And then I'm going to square root that whole answer. And I get 220.63, which means it's 220 newtons when I pay attention to significant figures. Now I said you'll also need an angle for this. So the angle is always tan, because you figured out an x and a y. So you're going to do the tan function. So tan of my angle is the opposite side, which is the y. Again, what you're finding is this angle. So the opposite side is going to be the y. So it's 126.55 over the x, which is 180.63. And so my angle then, 126.55 divided by 180.63. Second function, tan, and my answer, is 35 degrees. So it is exerting a force of 35 degrees to the horizontal. Now here's what I want you to notice in this, okay? Here's what I want you to notice. When I figured out my total force of the wall, it was the same as the force of tension. It should be. Because if the force of tension is working this way, then the force of the wall is going to have to work exactly opposite to that in order to counteract it. If there was more force of tension, it would be pulling the rod up. If the wall had more force of tension, it would be pulling the rod the other way. And again, the angle is the same as the angle that the cable made. And again, it should be. So that's how you do a sign question. Pay attention to where the mass of the thing hanging is. In this case, it was hanging here. If the sign or whatever is hanging off of the rod was hanging down here instead, so you had, a sign just hanging off of the end, then when we did the calculations, rather than for force of gravity, rather than being the R, rather than it being only halfway, it would have been the full distance of the rod. So just pay attention to that. So you guys should try number 33 on page 501. It is one like the sign one. So try page 501, number 33, and see how that goes. All right, we'll talk to you again soon. Bye.